All right. In the last video, so this is another advanced, something you really don't need to know, but I just want to talk a little bit more about these quaternions. We started them in the last one, and we said basically a quaternion looks like a number plus a three-dimensional vector. And the multiplication rule is kind of a combination of the dot product and cross product. So it's x naught y naught minus x dot y. That's the real part. And then the vector part is x naught y plus y naught x plus x cross y. And we said last time that this is basically as good as you get from a multiplication standpoint, except it's not commutative. So that's the one bad thing, but it is associative, which is the most important thing is distributive, but you almost don't even write something down if it's not distributive. So it's associative, which is the most important, and the surprising thing is it's actually what's called a division ring, meaning I can do 1 over one of these things. Winds up being, switch the sign, so just like conjugate, so take the conjugate just like you would for complex numbers, and then divide by this guy squared. So anyway, so we talked about those and just kind of the basics of the algebra last time. This time I want to tell you geometrically why were these things sought after to begin with. And on a little side note, this whole thing is parodied. Parodied. And Alice in Wonderland. So Lewis Carroll was actually a mathematician by trade, and I mean he just wrote fantasy books on the side. Of course, he was a lot better at fantasy books than he was at math, so that's what he's remembered for. But the whole Tea Party scene, and we'll talk about it a little bit when we actually get to it. This whole thing is a parody of the construction of the quaternions. So Lewis Carroll thought that numbers should just be one-dimensional things. He didn't like the idea of even complex numbers, much less quaternions, and so he kind of wrote this whole thing as a parody of people trying to make higher dimensional numbers. But anyway, so let's go back to real numbers, and we're going to think about what plus and multiply mean. So if I take a particular number, like say 5 or something, and think about the function like f of x is 5 plus x. So what does this function do? Well, this is translation by 5 to the right. So that's kind of what we're going to do. We're going to go back and rethink our arithmetic operations. We're going to think about them in terms of what do they do to the line itself. So if I have my real line, if I think about the number 5, well, adding 5, what it does is it moves everything on the line over by 5, which translation is really kind of the only thing we can do to one dimension. The other thing we can do is reflection. That's the only other symmetry the line has, and that's multiplied by -1. So, well, we've already got all the symmetries of the line, or all the ones that don't change length. So what does other multiplication do besides multiplication by -1? Well, multiplication usually either stretches or shrinks, depending on how big the number is. The line. So the word you had back in geometry, this is a dilation of the line. So, yeah, if I think about like f of x is, say, 3 times x, what that does is, well, it doesn't move the center of the line, but everything else kind of stretches out by a factor of 3. If I did half x, well, then everything would kind of shrink up by a factor of a half. But, okay. So for just regular one-dimensional numbers, addition turns into translation, multiplication turns into either stretching or shrinking. Okay, so no big surprises there. What about when we get to 2 dimensions? Well, addition is still just translation. For example, if I think about the function, I'm just going to pick a random number. Say f of z is z plus 5 minus 2i. Well, this function translates the plane over 5 and down 2. So here's 5, so it goes over 5 down 2. So the whole plane just gets moved like that. Okay, so that's easy. The trickier one is multiplication, and that was one thing that when people first did complex multiplication, they were a little scared of what was going to happen. It didn't really make a lot of sense. But back in trig, we learned there was a polar form of complex numbers, which you write a z as being r times e to the I theta, which if you multiply by r, just the r by itself, this is that same stretching and shrinking the plane that we had in one dimension. So like if I have, here's a triangle, if I multiply by 2, it's gonna pull that triangle out and make it bigger, right? So that one is exactly what we already think it should be. What if we multiply by e to the I theta? Well, you learned back in trig that if I go e to, I don't know that we actually use e to the I theta in trig. Now that I think about it. So it winds up e to the I theta is equal to cosine theta plus I sine theta. This we definitely used in trig. Okay. So, but the important thing we learned was that if I take 2 of these guys, so let's call those theta 1, and then another one, cosine theta 2 plus I sine theta 2, what happens is you add the angles. Theta 1 plus theta 2, I sine theta 1 plus theta 2. Okay. Or in other words, well, what did the first one do to the second one? So here was my second. So say here's theta 1. Here's theta 2. So if I do theta 1 plus theta 2, like wind up there or something. What multiplying this guy took the second one and rotated him an extra theta 1. So that's actually what multiplication by cos theta plus I sine theta is. This rotates the plane by theta. Okay, so we get a really nice picture. So these arithmetic operations we have, they all have geometric meanings in the complex numbers. So our addition corresponds to translation, which that one's kind of obvious. Multiplication, well, there's kind of 2 parts to it. If I multiply by the magnitude, so the r, This is my stretching and shrinking, just like I had back in one dimension. And if I multiply it by the direction, the cis theta, that rotates the plane by theta. So these are, these operations of multiply and add, they aren't just some random algebraic thing. These are very geometric operations. And basically, everything you would want to do to the plane except reflect it. We don't have reflections anymore, but we have translations and rotations, which is, that's, that's huge. And as far as that goes, we actually still do have reflections too. We just need to make up a new arithmetic operation. We did this back in algebra. It was complex conjugate. So this conjugation is reflection. This one happens to be reflection about the real axis. So in other words, the x-axis. But you can make any reflection you want to by combining this one with rotations. So all of your geometric things you wanted to do to the plane back in your high school geometry class, translate, rotate, reflect it, you can do it all with these arithmetic operations of add, multiply, and complex conjugate. So that's great. So the search began for R3 because this is the world we live in, right? And so it looks like I may have to turn this in two parts. I've only got about 10 minutes left. But anyway, the idea was, well, if we add vectors in R3, that's translation. That's easy. So the question is, how can we multiply vectors in R3 so that multiplying will turn to three-dimensional rotations? And so people started looking for this. The problem is there's not enough space in R3 to do it. Because if I think about, well, in R2, when I was rotating R2, there's really only one thing you can do, is go around in a circle, right? So that's kind of one dimension worth of operations. And then if you add the stretching and shrinking, so that's one dimension worth of operations. So I have two dimensions, which is the same as the dimension of my space. So I can reasonably hope to do this. Well, if I'm going to think about multiplying, one dimension is still going to go for stretching and shrinking. So I need one dimension for that. What about for three-dimensional rotations? Well, three-dimensional rotations, I actually need 4 dimensions just for the rotations themselves. So let's think about why. Well, if I want to do a rotation in 3 dimensions, first thing I have to do is I have to tell you, you pick a particular line that you're rotating around. The direction of this line can be any direction in 3D space. So I need 3 dimensions just to tell you what axis I'm rotating around. And then I need one more dimension to tell you how far I rotate. So am I rotating 90 degrees or 45 or whatnot? So I need 4 dimensions worth of stuff just to tell you a rotation. So there's no way I can possibly describe all. So if I want to possibly try to describe all 3D rotations, well, there's no way I can do that with some sort of three-dimensional multiplication, because to describe this, I need at least 4 dimensions worth of stuff, right? I can't describe 4 dimensions worth of stuff with only 3-dimensional space. So at the outset, it kind of looks like I'm up a creek. I mean, especially when I think, well, if I really want this to be multiplication, 1 dimension needs to go for stretching and shrinking. I need like 5 dimensions. I've only got 3. So anyway, so that's kind of what started Hamilton on his quest. He's asked, is there some sort of multiplication or something like multiplication on 4-dimensional space that gives 3D rotation? I mean, that's the right dimension for it. You need 4 dimensions to get 3D rotation. So is there a way you could actually build it? And the answer, of course, is going to be yes. It's going to be something related to the quaternions. But I actually have to go to class, and so I'm going to stop here. So I guess we'll record this in 2 parts. But thanks for listening.